Good morning, everyone. So let's start with the generator protection. Now, a generator could be a part of a generator could be it could be a part of water turbine based hydropower station, water turbine based hydro power station, or gas turbine based power station, gas turbine based power station, or steam turbine based thermal power station, steam turbine based thermal power station, or nuclear power station, or nuclear power station. Now, in all the above installations, the protection of a generator presents a very challenging problem because of its connections through to three different sides, as shown in the figure. On the one side, it is connected to the prime mover. As you see, on the one side, it is connected to the prime mover. On the other side, it has to run in synchronism with the grid because of its connection to the power grid. And on the third side, it is connected to the DC excitation. So it is thus obvious that the generator protection is very complex compared to the protection for the other elements of the power system. Now, in this case, what we discuss the protection of large, that is steam turbine based turbo alternators of capacity 200 megawatt and higher. So we will discuss the steam turbine based turbo alternators. Steam turbine based turbo alternators of capacity greater than 200 megawatt. Now, as you see, in case of fault on the turbo alternator, it is not enough to open the main circuit breaker which is connected to the power grid. Let us suppose that when the turbo alternator driven by the steam turbine is tripped, the following must be done. So, the turbo alternator driven by the steam turbine is tripped, so following must be done. Like what needs to be done? So, first one is steam supply to the turbine is stopped or bypassed. So, what we have to do? When the turbo alternator driven by the steam turbine is tripped, so in that very case, what we have to do? Steam supply is stopped. Steam supply to the turbine is stopped. Now, second, firing of the boiler is stopped. Firing of boiler is stopped. Then again, coal mills are stopped. Coal mills are stopped. Again, coal supply to the coal mills is also stopped. So the coal supply to the coal mills is also stopped. Then in the then field circuit of the alternator is interrupted. Field circuit of alternator is interrupted. Then the field coils are connected across the resistor to dissipate the energy. That is, field coils are connected across the resistor. Field coils, these are connected across the resistor to dissipate the energy. Connected across the resistor to dissipate energy. Then alternate is kept running at slow speed with the help of the bearing gear till it cools down uniformly. So alternator is kept running at slow speeds. Alternator is kept running at slow speeds with the help of bearing gear. With the help of bearing gear till it cools down uniformly. Till it cools down uniformly. To avoid uneven expansion. To avoid uneven expansions. Now, putting back the alternator on the line is actually rather a slow process because all the parameters, that is the temperature, then we will have the pressure. So it has to be progressively built up to avoid the thermal shock, resulting in the uneven expansion, which might cause the unacceptable vibrations. Which might cause these vibrations. So, therefore, the unscheduled outage of thermal power station is avoided as far as possible. Unscheduled outage is avoided as far as possible. So we have to keep in mind that the modern large turbo alternators is a huge mass which is rotating at a very high speed, that is 3000 RPM. So the modern alternators, they are actually huge mass rotating at a very high speed. That is, modern alternators, huge mass rotating at a very high speed of nearly about 3000 RPM in a very small air gap. So the air gap in that very case is very small air gap. Now, so apart from the large electrical energies involved, there is the tremendous amount of mechanical energy in the form of the movement of inertia of rotating mass and the resultant forces on the shaft, the rotor body and the stator structure. So, any slight increase in the temperature or uneven heating of the rotor or uneven heating of the rotor. Any slight increase in the temperature or the uneven heating of the rotor, it causes the eccentricity, and because of the high speed rotation, small air gap, the symmetry get disturbed. So it causes the eccentricity, and which gets increased because of the high speed of the rotation and small air gap. So the entire system has therefore to be run in a very narrow range of various parameters like temperature, pressure. It should be run in the very narrow range of the parameters, like we will have the temperature, pressure, then we will have displacement, flows, voltages, displacement, flows, voltages, currents, power factor, and so forth. So the operation outside the specified parameter may cause a substantial decrease in the life of the equipment. So, since, as you know, the fact that the power station equipment represents a very high investment of money, so the operation of the power plant is very closely monitored and controlled. So it must be monitored and controlled. Very closely monitored and controlled. You can say that the running the large power station is like the flying a supersonic jet aircraft without any forced landings or crashes. Now, the figure shows the complexity of the turbo alternator in more detailed way. We have here a figure which shows the complexity of the turbo alternator in a detailed way, as you have read about this this turbo alternator. So I think you must be knowing the various things involved in that. So I think I assume that you know all these things that you have read in your power system also. So this is actually the this diagram actually illustrates the complexities of turbo alternator in a very detailed manner. Now we will discuss the electrical circuit of a generator. And the electrical circuit of a generator is very simple in spite of its complexity which is involved in that. So figure here shows the various circuits of the generator. Now from this figure, as you know, as this figure, it is seen that the generator is never solidly grounded here. The generator is never solidly grounded. So if it is solidly grounded, that is, generator is never solidly grounded. Solidly grounded means that the resistance is equals to 0. So if it is so, the single line to ground fault current would be dangerously very high. So single line to ground current would be very high if the generator is not solidly grounded. It is solidly grounded. So to prevent that, it is not solidly grounded, because otherwise the single line to ground fault current would be very high. It would be dangerously very high. So apart from the high value of the fault current, the resulting asymmetry in the rotating magnetic field inside the generator, it would cause the unacceptably large vibration and result in the mechanical damage to the rotor. So what happens when the current increases? Apart from this high value of the current, what happens due to this single line to ground fault and the large value of this fault current, this asymmetry in the rotating magnetic field inside the generator would increase, asymmetry in the rotating magnetic field because of this fault current, increase in the fault current, asymmetry in the rotating magnetic field inside the generator, in the rotating magnetic field inside the generator it would actually cause the large vibration and result in the mechanical damage to the rotor. It causes the large vibrations, unacceptably large vibrations and mechanical damage to the rotor. Mechanical damage to the rotor. So, in order to limit this, the short circuit current, what we have to do? The neutral of the this generator is grounded through a resistance. The neutral of the generator is grounded through a resistance, and in order to get a practical value of the grounding resistance, it is connected through a step down transformer, which is also known as the grounding transformer. So the grounding transformer is used. So this thing you should take into consideration, that generator is never solidly grounded. Now the power plant has a very large, that is a sizable auxiliary electrical load of its own. So as you know that the power plant has the sizable auxiliary load of its own, and this is of the order of 10% of the power rating of the generator. 10% of the generator rating. Now this is supplied through a unit auxiliary transformer. In this figure it is shown here, the unit auxiliary transformer. So this is supplied through the unit auxiliary transformer, which is also known as UAT, and it must be taken into consideration that these auxiliaries require power even before the generator can be started, run up to speed and synchronized with the grid. So these auxiliaries are required. These auxiliaries are actually required even before the generator can be started, even before the starting of the generator, then run up to the speed and synchronized with the grid. Run up to speed and synchronized to grid. So there is the switching facility to energize this unit auxiliary transformer directly from the grid. So there is actually the switching facility to energize this UAT directly to the grid. So that thing is required. So switching facility to grid is there in case of these auxiliaries. In case of these auxiliaries. Now, one more point. Now the rotor of the generator houses a field winding, as you know the fact that the rotor of the generator houses a field winding, because as you know the fact that there are many advantages of field winding on the rotor. So the rotor of the generator actually houses a field winding, and a simple DC generator which is mounted on the turbo alternator shaft feeds that particular field, and the DC system is kept floating with respect to the AC ground, that is neither the positive nor the negative terminal is grounded. And the field interrupter and the arrangement for the field suppression is also shown in the figure. Field interrupter and the field arrangement for the field suppression is also shown in that very case. So as you know the fact, the rotor houses the field winding, and a separate DC generator which is actually mounted on that particular rotor, which is mounted on the rotor, a turbo alternator feeds the field, and DC system is kept floating with respect to the AC ground, that is neither positive nor negative terminal is grounded. And also we will have, in this case we will have the field interrupter and we will have the field suppressor, which is also shown in the figure whenever this happens, whenever the fault happens. So this actually shows the electrical circuit of the exciter of the generator. So this is the electrical circuit of the exciter of the generator. Electrical circuit of exciter of the generator. It contains the field interrupter and the field suppressor. Now we'll discuss the various faults and the abnormal operating conditions. So in addition to, we will have the electrical faults are there. In addition to the electrical fault, a generator goes through many abnormal operating conditions which need to be understood, because we have to must differentiate between what is an abnormal operating condition and what is fault, and then we can use the protection circuit for that very case. Now the figure, in this figure, it shows the hierarchy of the electrical faults and the abnormal operating condition. Now we will see, first we will have the electrical faults. Now in the stator we will have the fault on the three-phase stator winding, and on the rotor field winding, fault on the that is field winding. So what type of fault which occurs on the stator, that is three-phase stator winding, we will have the phase fault, we will have the interturn fault on the same phase, and we will have the ground fault. So in this, under the stator we will have these three type of faults: phase fault, interturn fault on the same phase, and the ground faults. And on the field winding, that is DC, we will have the short circuit to ground. So these are actually the electrical faults on the turbo alternators. So now second here figure, this diagram here shows the abnormal operating conditions. So here we will have the abnormal operating conditions. Now under the abnormal operating conditions, so abnormal operating conditions can be electrical and it can be mechanical. Now under the mechanical abnormal operating condition, we will have the loss of the prime mover. When the prime mover starts, that is its speed decreases, the speed of the prime mover decreases. So the loss of the prime mover because of some issues and the overspeeding, the speed of the prime mover will increase. Now this is in case of the mechanical. And under the electrical we will have the stator. Under the three-phase stator winding, we will have the abnormal operating condition, that is if the unbalanced loading is there. In all the three phases the loading is unbalanced. And under the field winding we have the loss of excitation. So these are the abnormal operating conditions. So under the various faults and abnormal operating conditions, we have discussed the electrical faults, that is stator, three-phase stator winding, rotor field winding. Under the stator we have the phase fault, interturn fault on the same phase, ground faults. And under the rotor we have the short circuit to ground. So these are the electrical faults on the turbo alternators. And under the abnormal operating condition, we will have the electrical abnormal operating condition. Under that we have a stator, three-phase stator winding, and the unbalanced loading is there. And then it is an unbalanced, this is abnormal operating condition. Under the rotor, that is the field winding, we will have the loss of excitation. Now under the mechanical we will have the loss of prime mover starts rotating and then overspeeding. So these are actually some of the faults and abnormal operating conditions, and we have to take into consideration while devising this protection strategy for this. Thank you very much. Now we can discuss the various type of faults and the protection strategies in the next lecture. Thank you.